Dear student, welcome to my channel. Topic of this video is bottom-up parser. This is the third video on the parser topic. In this video, I am going to explain CYK or CKY bottom-up parser. It is also known as COCKE-YOUNGER and KASAMI parser. Now let us start. It is a bottom-up parsing method for context-free grammar. It is based on dynamic programming concept. It requires grammar to be in CNF form, that is Chomsky normal form. Dynamic programming algorithm requires the context-free grammar to be rendered into CNF because it tests for possibilities to split the current sequence into two smaller sequences. So when we are solving the problem, these things will be clear for you. Any context-free grammar that does not generate the empty string can be represented in CNF using two production rule of the form. Capital A is given BC, that is A, B and C are nothing but two non-terminals. So in every rule, right hand side there will be two non-terminals, or capital A is given small a or terminal. CYK parser is efficient for parsing language that can be represented in CNF, which systematically explore all the possible parse trees. It is particularly useful for parsing ambiguous grammar and ensuring all potential parsers are considered. Now this is a CYK algorithm, so I will explain this algorithm with the help of example. Now for simplicity, I have taken whatever the problems they have the grammar in CNF form. So to convert the grammar to be in CNF form is very easy, but we can get in NLP directly the grammar in CNF form. Now this is the example. This is nothing but CFG is represented, that is context-free grammar is represented by T and SR, where T is terminal, N is non-terminal, S is start symbol, and R is nothing but the production rule. So terminal are a pilot likes flying planes, and these are nothing but non-terminal, which is S, NP, VP, VBG, NNS, VBZ, DT, NNJJ. So NN is nothing but singular noun, NNS is nothing but the plural noun, VBG is nothing but the verb in a gerund form, for example, which ends generally in ing, like walking, swimming, running. VBZ, present tense third person singular verb, and JJ is adjective. Start symbol, noun phrase, verb phrase. This is the start symbol S, production rule, and you can observe that on the right hand side of the production rule, two terminals are there, like A given BC, or it will give only one terminal like this rule. So the grammar is in strictly in CNF form. Now we require to parse this tree using the CYK algorithm. Now if we see as a human, these lines has a two meaning. A pilot likes flying planes, or pilot like to fly in a plane. So there are two ways, two meanings are there. So when we parse this given statement, we are also generate the two trees, parse trees, because ambiguity is inherent present in a natural language. So a pilot likes flying planes, whatever words is given in statement we require to write down like this. Make a matrix 0 1 0 2 0 3 0 4 0 5 1 2 1 3 1 4 1 5 2 3 2 4 2 5 3 4 3 5 and 4 5. Now first we require to use the CNF rule, which is nothing but A is given the terminal, and whatever the diagonal values we are filling with the terminal rule. So DT A, for example, A is there, so right to left DT is there. Next is pilot, pilot is from NN, then next is likes. Now likes is for VBZ. Now flying comes with the JJ and VBG also, because it acts as a gerund form as well as the adjective, and this is nothing but planes is nothing but NNS. So whatever the diagonal values we are filling with the rule of the form, capital A is given the small a, that is nothing but all terminal value. Now all that inner values are filled with the production rule form, the A given capital BC. Now 0 2 1 3 2 4 3 5 we are going to fill. Now here we are using the dynamic programming concept. So in dynamic programming we require to split into the two subparts. So 0 2 is split in 0 1 and 1 2, 1 3 is split into 1 2 and 2 3, 2 4 is split into 2 3 and 3 4, and 3 5 is split into 3 4 and 4 5, and the answer of this it used to calculate the answer of this. This is nothing but the programming concept behind the dynamic programming, that is we are first solving the small sub problems and we are using that solution to find out the solution for the bigger sub problem, and this procedure will continue. Now we can successfully parse the tree when at last when we are generating the start symbol here. So if we don't generate the start symbol as, that statement is not accepted by the language. Now 0 to, we require to this into two subparts. So possibility is only one is 0 1 and 1 2, 1 2 1 3, sorry 1 2 2 3, 2 3 3 4, 3 4 4 5. Now we require to write down in 0 2 0 1 dt is there, and in 1 2 NN is there. So we require to check the rule that dt and NN is present or not. So yes, dt and NN is present, and which is nothing but noun phrase. So noun phrase is there. NN and VPZ not present, nil. If not present, we are writing the nil. Now we require to check the combination of VBZ VBG is there, no. VBZ JJ is there, no, nil. Now VBG NNS is there, VBG NNS, yes, VP, and here JJ NNS is there, yes. So see, the words are same, but we are generating the two different phrase. That is, one is the verb phrase and second is the noun phrase. Now for this we can generate immediately trees to understand. So now see, for 0 2 we are getting the noun phrase, and for 3 5 we are getting the VP and NP phrase. So we can draw the diagram, that is NP, determiner and NT, a pilot, VP, and one is NP. So words are same, but it is represented as gerund form and it is represented as an adjective form. So here we can see that different possibilities of different parse tree can be generated. Now we have to find out which next value, 0 3 1 4 2 5. Now 0 3 we require to divide the problems into the two subparts. Now two possible paths are, one is 0 1 to 1 3 or 0 2 to 2 3. For 1 4 1 to 2 2 to 4 or 1 3 to 3 4, 2 5 2 to 3 3 to 5 or 2 to 4 4 5. So these paths are there. Now we are writing all the answers we are getting from the small sub problem. So generally when nil comes on the right hand side or left hand side, the answer is nil. So here answer is nil. NP VPZ not present, nil, nil. Now here it is nil. Now we will check this. VBZ VP produce the verb phrase, and VBZ NP also produces the verb phrase. We can see that VBZ VP and VBZ NP, VBZ VP and VBZ NP. So here we, for simplicity, we have given VP1 and VP2, but we can directly write VP also. Now see, VP1 and VP2, two verb phrase get generated. One because intermediate, here it is VP and here it is NP. Now we will go for the next. Now up to this we have calculated. Now next diagonal 0 4 1 5. Now 0 4 1 5, three ways are there, 0 1 to 1 4, 0 2 to 2 4 and 0 3 to 3 4. That is 0 4 we require to split into two parts. So three combination can be possible, and similarly we can split the 1 5 into three possible combination. After that we require to take the solution from the small sub problems we already calculated, and we are writing the answer. Now nil, 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 so the answer is nil. So here dash dash is coming. Now only we require to solve this last cell 0 5, and here the S must come, otherwise the statement get not passed. So here the tree is not generated. Now the last one, that is 0 5. Now require to 0 5 to divide into two parts. So first part is 0 1 to 1 5, 0 2 to 2 5, 0 3 to 3 5, 0 4 to 4 5. We will write down all the previous sub problems, and here we can find out that NP VP1 and NP VP2, NP VP, we have given 1 and 2, otherwise it is VP only. So we are getting the 2 start symbol. So it indicates that it has 2 parse trees. Now we will draw the diagram. Here S1 and S2. Here change comes this VP1 and VP2, because here this is a VP and this is the NP. So if you observe the problem from the start, you will immediately come to know. because as a human also we can find out the two meaning for this statement. Now just all diagrams are shown step by step. First you require to fill all the cell of matrix, and after that you try to draw the diagram so the things will be clear for you. So this is the second and this is the last one. Now we'll see the next example. G is TNSR, time flies like an arrow. S, NP, VP, VST, PP, V, determiner, NP are nothing but the non-terminal symbol, and these are nothing but the rules. You can find out that all rules are in the CNF form, and this is nothing but the terminal. Statement is time flies like an arrow. These are the terminal rule and these are the non-terminal rule. Next we will create a matrix and we will fill the diagonal cell by seeing the rules, in which right hand side only terminal symbols are there. So as two combinations they are there, it is likely chance that there are different parse trees. Next we will calculate 0, 2, 1, 3, 2, 4, 3, 5, and every time we require to divide this into two subparts. So 0, 1, 1, 2, 1, 2, 2, 3, 2, 3, 3, 4, 3, 4, 4, 5. Now see, same as previous problem. So for 1, 3 nil, 2, 4 nil and 3, 5, that is nothing but 3, 4 and 4, 5 combination. So NP and arrow, that is noun phrase, get generated. Now we will see this 0, 2. This 4 combination can be possible: NP, 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 VP, VST, NP and VST, VP. So NP, VP create the S1, because see why the start symbol get generated, because time flies can be the correct statement. S2, VST, NP, time flies. Now here we can see the chances of the multiple parse tree get generated. Now here the time flies same, but the finally is noun phrase, it is not converged to the start symbol, so this can be intermediate. Now we can see the diagram for this. This is nothing but noun phrase, that is an arrow, and for this one is S1 noun VP, VST, NP, and this is converged to the noun phrase. So 3 ways can be possible. Now we can go for the next diagonal, that is nothing but 0, 3, 1, 4, 2, 5. Again we require to divide this into the two sub problems. So one possible way is 0, 1, 2, 1, 3 and 1, 3, then 0, 2 and 2, 2, 3. So if any one of the nil comes, so generally answer is nil, but still we have to check. Now we'll see this PVP. See, PV NP possible, VNP is possible. So PNP is creating the PP. You can see that PNP creating the PP and VNP is creating the VP. So we can draw the diagram. This NP comes from our previous answer, so we require to trace back that. So this likes get added. This is common, but one with V and one with P. Now we'll calculate the next value. Now we'll calculate 0, 4 and 1, 5. So divide the problem into such a way that two subparts. So one possible is 0, 1, 1, 4 or 0, 2, 2, 4 or 0, 3, 3, 4. Nil, don't check, nil, don't check, nil, don't check. But here we can see that again start symbol comes S3, NPPP and VPPP. So we require to check this combination NPPP is there or not in rule. NPVP, then VPPP and VPVP. So when we see these chances, we can find out that it can generate. Now again his S3, that is nothing but start symbol gets generated. We will see in the diagram. Now this is nothing but NPPP, so we require to check all the previous answer. This is with the VP, and see the start symbol get generated, and if you see the statement flies like an arrow is also a valid statement. That's why again here S3 gets generated, that is start symbol gets generated. Now we will go to the last. Then here it is nothing but 0, 5. So possible combinations are 0, 1, 1, 5. Then 0, 2, 2, 5. 0, 3, 3, 5. 0, 4, 4, 5. So we will check if nil is there. We will not check on the left or right. Otherwise we will see all the combination. So these 4 combinations are getting here. And here we can see that start symbol gets generated, but 2 start symbols means 2 parse tree can be generated for this statement. This NP is not useful because at last it should converge into the start symbol. So I have drawn for NP, but there is actually as such no use. But only we can see that the variety types of ambiguity comes into the intermediate state. So this is NP. We will observe only for S5. So this is the S5. And this is, that's why I have not drawn this diagram also. There is PP because it's similar, only the change is there. So important is what S3 and S4 and S5. S3, S4 is given because lot of source symbols get generated in between, that's why. So see this VST time as above, that is nothing but the VST is nothing but the duration. So time comes into that category. Here it is by mistake, it is time. So maybe a very minor mistake may be there in drawing because it's not easy to draw, but with this matrix you can check and you can backtrack and you can draw the parse trees. So I have shown again. Now this is the exercise for you people. This is a grammar is given. It is strictly in CNF form. Take a statement, she eats a fish, and you can parse the statement, or you can take the statement she eats a fish with a fork. You can try that for that statement also. Next is, this is again example, another example. You try with this. Fill the man with the trust. Here also this SVP is there, but that is okay in CNF form if it reach to the one non-terminal, because sometimes in language it is very difficult to write down those 2 strictly symbols. So this is also okay. This is exceptional. You can take this also. So we can see that the drawback of this algorithm is that it can generate the multiple parse trees. So if we have already seen in previous videos that this number of parse trees, as the number of words in a statement gets increased, the number of parse trees generated are exponential. That is called Catalan number. So which parse trees should be more probable. So that is nothing but the we are using the CFG, that is context free grammar, but that is nothing but probabilistic context free grammar, that is nothing but PCFG. So in the next video I am going to explain the PCFG probabilistic context free graph bottom up parser, in which we can calculate the probability of each parse trees and we decide which parse tree is more probable. So this is nothing but the drawback of this multiple parse tree gets overcome in PCFG to select which is the best parse tree. So I am going to explain that in my next video. So these are the references for this video. Thank you.